Welcome back, everyone. I'm Michelle Sanner, and today we are going to be talking about the particle model of matter. So I'm going to talk a little bit about the principles of the particle model, and then I'm going to show you a couple of examples in the lab. The first principle of the particle model is that everything is made up of particles. From the clothes you're wearing, the ground you're walking on, the computer screen that you're looking at, everything is made up of particles. Later on in the year, we're going to talk about some of these particles in particular, like molecules, atoms, and even the subatomic particles like protons, neutrons, and electrons. The important thing for you to know right now is that everything in the universe that's made up of matter is made up of particles. Particles are always moving. There's a couple of different types of movement that a particle can have. You can have translational, where you're moving from side to side. You can have rotational, where a particle is spinning. And you can even have vibrational, where the particles are just moving back and forth. These particles are always in motion. The only time where you wouldn't have any particle movement at all would be at what scientists call 0 degrees Kelvin, or absolute zero. And this is the theoretical state at which all movement for molecules ceases to be. Particles have spaces between them. Some types of particles like to be spaced really closely together, and some like to be spaced really far apart. You learned a little bit about the phases of matter, where particle spacing comes into play. Solids have tightly packed together particles. Liquids are a little bit more spaced out so they can flow easily around each other. And gases are the most diffuse. This room is full of gas particles right now, but they're not very close together. They're distributed throughout the three-dimensional space. When you heat up a particle, it moves faster. This is because the measurement of heat, temperature, is simply a measurement of the average kinetic energy of a particle. That is, a measurement of how fast those particles are moving. So hot particles move fast, cold particles move slow. A really common misconception, my mom always used to yell at me and say, "Shut the fridge, you're letting all the cold air out." Well, actually, you're letting all the hot air in, because heat is simply particle movement. Cold particles, on the other hand, move quite a bit slower. And this is reflected in the phases of matter, in the fact that an object like an ice cube at its coldest is in its solid form. You apply more and more energy to it, it becomes a liquid, it melts into a liquid, and if you boil it on the stove, suddenly you've got steam. You've turned your liquid into a gas, and particle spacing follows this pattern. In its warmest states, particles are farthest apart. In its coldest state, they're spaced more closely together, and they move more slowly. Particles are also attracted to each other, and depending on the type of particle, they're going to be either more or less attracted to one another. We'll learn more about what some of the principles of attraction are in later units, but for now, just understand that particles either have a tendency to stick together or not stick together quite as well. All right, so now we know what we're doing. Let's take it into the lab. All right, welcome to my lab. So first things first, we need to make sure we're demonstrating proper lab safety. So I'm going to start by putting my hair up, and I'm making sure that I'm wearing lab appropriate attire. I've got closed-toed shoes. I'm wearing clothes that cover my torso and my legs so that I'm perfectly safe in the event of any spills. So what I have for you here are two different temperatures of water. I've got some hot water that I heated up in a boiler and some kind of room temperature cooler water here. And we're going to see what happens when we add a couple of different substances to the water, see if the temperature changes anything. So here is my first substance. I'm using like a Country Time lemonade pink powder. So this demonstrates sugar, but I like that it had the color because this will allow us to see it a little bit better. So I'm going to add the same amount. I went ahead and pre-measured two different samples that are exactly the same. And we're going to dump them into the hot water and the cold water and see if there's any difference in terms of the particle movement. So here we go. Okay, so looking at the warm water here and the cool water here, let's see if there's any difference in how easily they're able to dissolve. Just going to stir this guy up a little bit. Got the hot water, and over here the cold water. And we'll see how well each of these dissolved. Well, this hot water looks pretty much completely dissolved. If I zoom in, you could see maybe just a few crystals there on the bottom, kind of out of focus, but this cold water, you could see quite a bit of particles there settled on the bottom. So this is kind of like when you get an iced coffee or something at your local coffee store. You may try to put in some sugar into your iced tea, and you'll notice that it kind of tends to pool up along the bottom. So there's some sort of difference between hot water and cold water and its ability to dissolve a substance like sugar. So take a second and think about why that might be. So we're going to try this demonstration again, the hot water versus the cold water, with a different substance. This time I'm going to use baking soda, and we're going to see how well it dissolves. Again, I've measured out the exact same amount, put the same amount of water, and we're just trying to see if temperature is a factor. We're dumping them in. Give the hot water a stir. Give the cold water a stir. And we're trying to see if temperature is a factor. Okay, so once I let the particles settle, what I notice is that the hot water here seems to have dissolved quite a bit more of the baking soda than did the cold water. So I wanted you to think about why that might be. What is it about the spacing in terms of temperature that allows the substance to dissolve better or worse in hotter or colder water? So take a second and think about why that might be. For our final temperature demonstration, we're going to look at the idea of particle movement. So I'm going to use some colored food coloring to put inside these two different temperature water, and we'll see if there's a difference at all in how they behave. So I've got my red food coloring, hot water right here, cold water over here. Just going to put 1 drop in each. 1, 1. What I notice is that there seems to be quite a bit more movement of the food coloring in the hot sample than there is in the cold sample. So this one right here, this is just good old room temperature water, and this is some water that I heated up in an electric kettle. So take a second and make an observation. What do you notice is the difference between particle motion in hot and cold water, and why do you think that might be? Don't forget to reference the particle model theory in your answer. So for my next demonstration, we're going to look a little bit about how the phase of the matter, if it's a solid or a liquid or a gas, kind of tells us a little bit about particle spacing. So what I have here is a Ziploc bag just full of regular tap water. I've tried to smush out as much of the air of it as I could. And up here in the corner, I have an alka-seltzer tab that I've separated out. I've separated because I don't want it to start a reaction yet, but I'm going to go ahead and get that reaction started. Solid alka-seltzer dropped in my liquid water is starting to give off bubbles. And those bubbles are filled with gas molecules. There's some sort of chemical reaction here that's causing the particles to turn from closely spaced together solids and medium spaced together liquids into far apart spaced gases. So if I turn my bag sideways, I had gotten all the air out of my bag, but you can see, make sure it's sealed real tight. You can see I'm starting to get fuller and fuller as the gas expands here in my tablet. And so where I started off with absolutely no gas in the baggie, you can see my finished product has quite a bit of gas. So my question is, what does this mean for particle spacing? What happened to the particles in this chemical reaction as they went from solid and liquid into a gas form? Take a second and see if you can answer it, and tell me how it ties in with the particle molecule theory. And tell me how it ties in with the particle model theory. Well, we've already seen what happens when a chemical reaction causes a liquid and a solid to convert it to a gas form. So now I'm going to take a gas and I'm going to heat it up a little bit and see what happens. Earlier today, I put a balloon, like a half-filled balloon that I blew up and put it in my freezer. And I'm going to take it out now, and we're going to take a little observation look at it. Okay, here's my frozen balloon. I just pulled it out of the freezer. I could barely get it in the freezer when I first put it in, but now, as you can see, it's quite a bit smaller. So we're going to watch it, just observe it for a second. As it starts to increase in temperature, I'm going to warm it up with my hands. I'm going to warm up the gases that are inside this balloon. And as I do that, their particle spacing starts to change. Their kinetic energy starts to increase. That is to say, as heat is applied, the particles move faster and faster and faster. We talked about the rotational, translational, and vibrational particles that are movement that these particles have. And that's happening inside the balloon. In fact, what's making the walls of the balloon expand is the pressure of many different particles bouncing off the inside walls of this balloon. So my balloon got a teensy bit bigger. So I'm going to see if I can really induce something more exciting. I'm just going to add a little bit more heat to this reaction, and we'll see if this changes anything. See the gas is starting to expand a little bit more. And they expanded to the point where they simply couldn't be contained by the balloon anymore. So take a second to reflect on what you just saw and why adding heat to some particles might cause them to move faster and faster and faster. Don't forget to reference the particle theory of matter in your answer. All right, take good notes, and I'll see you next time. Remember our first demonstration where the red food coloring went into the 2 different temperatures of water? Take a moment and write down your observations. What did you notice? What did you see? Think about visual and other forms of information that you learned. Remember our second demonstration? We mixed sugar and baking soda in 2 different temperatures of water. So tell me, what observations were you able to make from this? What principle or principles of particle theory are modeled by this demonstration? Why does temperature affect how well a substance can be dissolved in water? And what does this tell you about particle spacing, about particle movement? Pause the video and write down your responses. Think back to our demonstration of the alka-seltzer in the bag of water. What observations were you able to make? What principle or principles of particle theory are modeled by this demonstration? Why is it that the bag expanded in size, and what could have caused this if the temperature remained the same? Pause the video and take a moment to answer these questions. Our final demonstration was the balloon. What observations did you make as the balloon was moved from the freezer to room temperature and finally heated with a flame? What principles of particle theory are modeled by this demonstration? Why did the balloon pop? And why was the balloon smaller in the freezer than it was at room temperature? Pause the video and write down your answers now. That's it for today. Next time we meet, we'll be talking about particle stickiness. We're going to do a hands-on activity for this, so you'll need to gather the following materials at home: 2 pennies, a glass of water, a small amount of cooking oil like vegetable oil, olive oil, or any other liquid cooking oil, droppers if you have them, but if not, no worries, and paper towels. Thanks for coming, and I'll see you next time.